Okay, so hi there folks, we're now in our next video in college algebra, and here we're going to talk about more about the operations on radicals. Specifically, we're going to talk about the division radicals. And similarly, in just like in multiplication, we're going to divide the video into two parts. First part of the video is to show on how to divide radicals with the same index. And on the next video, we're going to show how to divide radicals with different indices. So we're going to make use of this fact that the nth root of a divided by the nth root of b is equal to the nth root of a over b. Just take note the denominator must have no radical, no radical here. Okay, so no radical in the denominator. So we must find ways in order for us to delete the radical sign in the denominator. So let's proceed with the first example. So we have is the first example over here, and we want this cube root of 2 to be deleted. So if we try to first apply the formula. So what we have is, since we have the cube root of 5 divided by the cube root of 2, since both of them are both um, with an index of 3, so we can write it like this, 5 over 2. So clearly we cannot do anything with the cube root of 5 over 2, since we cannot do the division there. So we need to make the 2, okay, the denominator here, okay, um, we're going to delete the cube root with that denominator. Okay, so with that, we're going to find some number which is a power of 2 and which is a perfect cube. So we can see that 8 does the job. So that is 2 cubed, right? So we have a 1 here, 2 raised to 1. What we will need to do is to add up, okay, 2 raised to 2. Because by the law of product in our um exponents, we can add up the exponents if the bases are the same. Since the bases are the same, with which is 2, so 2 plus 1 is going to give us, it becomes the cube root of 5 times 2 squared. Anyways, we are rationalizing in this part. So this is the part where we're rationalizing. Okay, so thus what we have is 5 times 2 squared all over 2 cubed. So 2 cubed, we can cancel up the cube here and the cube in the denominator by having that. What we have is, if you want, we can distribute again the cube root. Okay, so we have 2 squared is 4, 4 times 5 is 20, cube root is 20, and we have the cube root of 2 cubed, which we can cancel clearly. So what do we have? What do we have here? So in the numerator, we cannot do anything with that, so that becomes 3 cube root of 20 all over, cancel this up. Therefore, what we'll have is 2. So this is our final answer for the number 1. So we have the cube root of 20 divided by 2. Okay, next number. Let's give another example here. So what we have is the 10 square root of 18 divided by 5 square root of 2. This is a number. Okay, this is not a index, not an index. Okay, next, so we'll do the operation. 10 divided by 2, rather 10 divided by 5 is 2 clearly, and then put them under 1 square root, 18 over 2 by our formula above. This will give us 2 square root of 18 over 2 is 9. Square root of 9 is equal to 3, so we have 2 times 3, which is equal to 6. And that's our answer for number 2, 6. Okay, I hope you understood that part. Next is we're going to continue with our number 5. Number 5 looks like this. So we have 15 square root of 5 divided by 5 square root of 5. So let's do the division. 15 divided by 5 is 3. What we have is square root of 5 over square root of 5. My goodness, this is gonna give us 3 times square root of 1. Square root of 1 is 1, so we have 3 times 1, which is equal to 3. And 3 is our answer for number 3. Okay, so our answer for number 3 is 3. Okay, so that's how you do division if the indices are the same. Now, the next part is, what if the indices are not the same? What will we do? So that's still number 3. Okay, so let's move on with number 3 here, or rather number 1 rather. Okay, for the letter B. So to divide two radicals with different indices, we will use again the fractional exponents, the concept of fractional exponents, and the laws of exponents, therefore. So for number 1, what we have here is a square root of 6 divided by the fourth root of 2. So we cannot apply the rule which is shown in our A, simply because they're not of the same index. So what we're going to do is just use first the laws of fractional exponents and laws of exponents in order for us to make them the same uh, the same index. So what we have here is, put them back in fractional exponents. What we have is 6 raised to 1 half. There's a 2 here, right? That becomes the denominator. And down below, what we have is 1 over 4. So we'll find the LCD of 1 half and 1 fourth. So you will eventually know that it's going to be 4. It's going to be 4 here also. 1 fourth is still 1 fourth. 1 half is going to become 2 fourths. So we're going to follow this on 1 half. So therefore, this becomes 6 raised to 2 fourths all over 2 raised to 1 half. Hence, we'll convert this on radicals right now. What we have is the fourth root of 6 squared all over the fourth root of 2. Okay, and 6 squared we know as 36, right? So we have the fourth root of 36 divided by the fourth root of 2. Okay, so since they are now of the same root, maybe we need some space here. We can simplify this via, okay, so what we have is the fourth root of 36 over 2. So again, we have a root on the second exponent. So we're going to find a power of 2, which is a fourth root. So that is 16, because 2 raised to 4 is 16. So we need to make this a 16. So how do we do that? We multiply this 2 by 2 raised to 3. That's 2 cubed. So that it will become 2 cubes times 2, which is raised to 1, which will become 2 to the fourth. So likewise, we'll do this also to the 36 to the numerator, which will end up will which will give us what numbers? Maybe we can separate them now. 36 times 2 raised to 3, and then what we have is fourth root of 16, which is we know as 4. So therefore, what we'll have is 2 raised to 3 is 8. 36 times 8 is going to give us what? 36 times 8. 24, 48. That gives us 288. So we have the fourth root of 288 all over 2. The 16 is take note, 16 is equal to 2 raised to 4. So we may write this or we may write this fourth root of 2 raised to 4, which will eventually end give us with 2, or give us 2. Okay, so we need to find something which is a perfect uh, fourth root, okay, for 288. So what number is a perfect fourth root of 288? Maybe we can eliminate some numbers first. Um, uh, let's find some number which is 16. Is 288 divisible by 16? Let's try. I think we need more space here. So this is our last step, right? So 288, is it divisible by 16? Since we know that 2 raised to 4 is equal to 16. So divide this by 16. So we have 1, we have 16 here. We have 1, 2, 8. So how many 16s are there in 1 to 8? I don't know. 80. Let's try 16 times, what? 16 times 8. 8, 48. 1, 2, 8. Yeah, that's correct. 16 times 8, that's 18. So therefore, what we have is, um, can we write it here? What we have is the fourth root of 16 times 18 all over 2. So what we'll have then it's going to be, we're going to extract the square fourth root of 16, which becomes 2. So therefore 2 fourth root of 18. But notice in our denominator we have a 2 also, so we can cancel this 2 and 2 here, ending up giving us our final answer, which is the fourth root of 18. Okay, and that's our answer for number 1 for letter B. Okay, so it's quite a lot of steps to do, but I mean, yeah, it's doable. It's doable. Okay, so therefore, we can say that the answer here of sorry, of 6 fourth root of 2, or rather square root of 2 divided by fourth root of 2 is equal to the fourth root of 18. Okay, let's proceed to the second number. Hopefully, it will not be as uh as long as the previous one. So what we have is cube root of 128 divided by the square root of 32nd. So again, let's make them, okay, let's make them of the same index. So what we have here is 128 raised to 1/3 all over 32 raised to 1/2. So what about that? The LCD of 1/3 and 1/2 is going to be 6, or 1/6. So sorry, this is 1/2. So 1/3 converted to sixth is 2/3, or 2/6 rather, and 1/2 converted to a denominator with 6 is going to be 3/6. So that will be our next line here, 128. That's 1/3. It's equivalent to 2/6. And in the denominator we have 32nd uh, raised to 3/6. Okay, and then what we'll have is we have the sixth root of 128 squared, some big number, and we have the sixth root of 32nd cubed, 32nd cubed, which is also a big number actually. Okay, now we would want to find some numbers, which is we can cancel it up with the sixth root, so that we won't need to square or to cube these numbers. These numbers are quite big actually, so that we can cancel them. Okay, so that we can cancel some of them. Okay, so how do we do this? Let's find the base, which is so small, which is a perfect powers of both 32 and 128. Actually, we will know that as 2, since we know that uh, 2 to the fourth is 16 from the previous example. 2 raised to 5 is going to give us 32nd. 2 raised to 6 is going to give us 64. 2 raised to 7 is going to give us twice of 164 is 128. So um, I think I think that will be enough for us for this number 2, because 128 is going to be 128 is going to be until here, and we have 32 is going to be 2 raised to 5. Okay, and so therefore what we can have is going to be like this. So we have the sixth root of 128 is 2 raised to 7 raised to squared. Okay, and then the sixth root of 2 raised to 5 raised to 3. And then by the power of the power law, what we'll have is the sixth root of 2 raised to 7 is 2 raised to 14. 2 raised to 14 is quite a big number. And then all over 6 over 2 raised to 15. Now, what we will do here then is quite some magic. We will find the factor of 14. We'll factorize 14 and 15 in such a way that we can cancel up 6 roots from that. Okay, we can cancel 6 roots from that. Okay, so how will we do that? We'll try to get things canceled up. So what we'll have is sixth root of 2 raised to 14 is equal to 2 raised to 6 times 2 raised to 6. Can't fit. Let's put it here outside or below. So sixth root of 2 raised to 6 times 2 raised to 6. So we have 12, 2 squared then. Then down below what we have is 2 raised to 6 times 2 raised to 6. This is 12 times 2 raised to 3. Hence, what we have is 2 raised to 6 is 2 outside, and then 2 raised to 6, 2 is outside. And then what we have is, what we have left is 6th root of 2 squared. And then outside again, we have 2. We extract this one here, extract also this one here. So 2 times 2, 6th root of 2 cubed. And then what we'll have is, clearly we can cancel up these 2's here, leaving us with 6th root of 2 squared all over the 6th root of 2 cubed. Okay, so we have the 6th root of 2 squared over the 6th root of 2 cubed, and we want to delete this denominator here, which is a rational. So we need to multiply this by 2 raised to 3 so that we can cancel up the 3. Okay, it will become 2 raised to 6, and which is the 6th root of 2 raised to 6 is 2. So multiply this also by 2 raised to 3. So what we'll have is actually equal to, um, they're all under 1 square root, right? So what we have is the 6th root of 2 raised to 5 all over the 6th root of 2 raised to 6, which will give us eventually, and this will be cancelled up. This will just be 2. What we'll have is 2, okay, 6th root of 2 raised to 5. 2 raised to 5 is equal to 32, and this is our answer for number 2. We end there with simplification. Okay, so that's again quite a lot. Sorry for the second number. So you need to practice this, especially the rationalization part of the number. Actually, we shall also need to do this, extend this. Okay, let's proceed to number 3. This is our last number for this. Let's have this one. Okay, number 3, we have the square root of 3 all over cube root of 2. Again, let's do the routine. So we have 3 raised to 1/2 all over 2 raised to 1/3. Again, the 1/2 is equal to 3 over 6, and 1/3 is equal to 2 over 6. Hence, what we'll have is 3 raised to 3 over 6 all over 2 raised to 2 over 6. Put them back in radicals. Then we have the 6th root of 3 cubed, and we have the 6th root of 2 squared, which is quite good in the eyes. Only in the eyes. We need to simplify that, my goodness. So, um, in simplifying that, we need to, oh, there's no numbers that we can get the 6th root of both in the numerator and the denominator, but we need to rationalize the denominator. So multiply this denominator by, what do we need? We need 2 raised to 4, so that this will become 2 raised to 6. So we cancel that. Therefore, we also do this in the numerator like that. Hence, this becomes 6th root of 3 to the 6th. Or, sorry, they shouldn't be like this. They should be 2 raised to 4. My goodness, my bad. Sorry. Um, Continue. 6th root of 3 cubed times 2 raised to 4 all over 6th root of 2 raised to 6. So we can cancel up the roots here, ending giving us 6th root of 3 cubed times 2 to the 4th, and we have 2 down below. 2 down below. Um, let's try to give some numbers here in which we're going to extract 3 cubed times 2 raised to 4. So 2 raised to 4 is 16. 3 cubed is what? 9, 27. 3 squared is 9. So 3 cubed is 3 times 9 is going to be 27. That's correct. So multiply them. 27 times 16. What is the number? We have 2. 12 plus 7 is going to be 19. 6 times 7 is going to be 42. So our answer is 3, 4, 3, 2. Okay, 4, 3, 2. Okay, so that's our answer, which is 4, 3, 2. Okay, so 4, 3, 2. The cube root of 4, 3, 2. as the sixth root of 432. Now we'll try to extract something from 432. The sixth root of 2 is what 60 sixth root of 2 2 fifth 2 raised to 5 is 32nd. 2 raised to 6th is 64. Let's try if this is divisible by 64. 432 divided by 64. We cannot do that. Uh 5. Let's try 7. 64 times 7. We have here 42. 7 times 4 is 28. That gives us 448. That's an overshoot. We cannot do that. What else? Let's try again. 27 times 14, just to double check. So we have 2, we have um 12 plus 7 is going to give me 19. 7 times 6 is going to give us this indeed 42. So therefore we have 432. So that's correct. If you know some numbers which can have a factor of a perfect sixth root of 432, so you may add up, you may write that in the comments below. But for now, the correct answer is the sixth root of 432 all over 2. Again, I'm not sure about the 432 number here. Okay, but the divisibility, maybe you can find some factor of 432, or if 42 is a perfect sixth root, so what number is that? So leave it in the comments below. So with this, this is the perfect time to end the video right now. So thank you very much for watching, and see you soon. Okay, thank you.